Welcome to Session 5.0, Thermal Performance and Climate Control. This EMSI training section covers energy basics on building thermal performance and climate control systems. Your presenter is Rick Mitchell. This module will give you an understanding of energy use in climate control systems and control measures for increasing building thermal performance in the residential, business and commercial sectors. Currently, the average main consumer of energy in Australian homes and in many businesses is the heating and cooling. Approximately 60% of homes in Australia now have an air conditioner installed. Cooling accounts for 38% of energy use in Australia homes, and HVAC accounts for up to 30% of the total energy bill in businesses and commercial buildings. There are three key types of modern HVAC technologies covered in this module. These are traditional, radiant, and passive technologies. The thermal performance of a building is often presented as a measure of its ability to keep or repel heat and maintain a steady, comfortable, internal ambient temperature. This is largely dependent on two things: the building's construction, being materials and design, and the external ambient temperature and solar gain. A quick way to make an estimate of the external ambient temperature is to refer to a climate zone map. The Australian Bureau of Meteorology's climate zone map breaks Australia down into 6 climate zones for simplicity, as defined by the Building Code of Australia. Understanding diurnal, seasonal and annual temperature and climate patterns is crucial to understanding where opportunities for energy efficiency in thermal performance are achievable. HVAC Technologies. There are a great number and variety of cooling and heating devices used in the residential and commercial sectors. The more common of these can be divided into 3 different categories: traditional, radiant or passive. Within this largely user-driven sector, many of the reductions in energy consumption will come from consumer behavior changes as well as efficient devices. Traditional technologies are the most common technologies used in homes and small commercial buildings. They include the traditional air conditioning systems that incorporate the refrigeration cycle, including split systems, ducted systems, and window wall units, and fan and exhaust technologies, as well as cooling towers for large commercial applications. Radiant technologies involve chilled beams, radiant heaters, and in-floor systems where cooling or heating is achieved by the transfer of heat by radiation. Passive technologies use natural resources to autonomously cool spaces with little to no energy cost. They include evaporative cooling, trom walls, and wind tunnels, such as Federation Square's Labyrinth system. These technologies will all be discussed shortly. However, first it is important to understand the basics around how heat is transferred. Thermal performance and heat transfer. There are 3 types of heat transfer. First, radiation, where the heat is transferred through electromagnetic waves. These waves are capable of traveling through space, for example, the sun's rays, which travel towards Earth. Visible light and gamma rays are also forms of radiation, and all objects will emit some type of radiation. Convection takes place when heated molecules move from one place to another, taking the heat with them. Heat can also be transferred from one object to another, or from one molecule to another through the process of conduction. As one molecule is heated, it begins to move and shake rapidly. As it does so, it passes some of its heat energy to other molecules around it. Through this process, all the molecules of an object pass heat from one to another until they are all hot. What is important to note here is that heat always moves from a hotter surface or object to a cooler one, or from a higher to a lower temperature. Areas also gain heat from objects within the space. Heat transfer can occur from air ventilation, infiltration or exfiltration, solar radiation and heat conduction through walls, windows or the roof, building occupants, equipment which is usually comprised of electrical appliances, and lighting. Thermal performance plays an important role in determining the demand on a cooling or heating system. To design a cooling system, the heat gain is calculated to determine the possible peak conditions. A vast number of factors can affect a space's ability to keep or repel heat loads such as orientation and solar gain, thermal mass, insulation, glazing, shading, and ventilation. Heat transmission, here represented as Q-trans, measured in watts, is equal to the product of the coefficient of heat transfer, total surface area, and the temperature difference across the material. Please note that the overall heat transfer coefficient, U, is also calculated as the reciprocal of the sum of the material's resistance. where the total resistance is equal to R1 plus R2 plus R3, etc. The total heat transfer coefficient would be 1 divided by the total resistance. Let's start to disambiguate some of that, starting with the coefficient of heat transfer, or U. Every material has different characteristics, and one of these characteristics is its ability to resist heat flow. The resistance, or the R value, is a measure of the temperature difference by which an object or material resists heat flow. Therefore, the higher the resistance, the better the thermal performance of the material. Every material has an R value, and there are many R value tables available from the manufacturers that rate the thermal performance of a material per thickness. When calculating the total resistance, you must add the R values of every material surrounding the space. For example, a roof can have a combination of an external air pocket, the roof sheeting itself, an internal air pocket, possibly sarking, an internal air cavity, ceiling materials, and insulation. Insulation is used to act as a barrier to heat flow. In general, the floors, walls, and roof of a building can be insulated to provide comfort during summer and winter. Good insulation has a high resistance, therefore a high R value, and a lower heat transmission or a low U value. Insulation acts as an additional barrier or additional R value to trap or resist heat in a space. Glass wool, which has an R value of 2, and fiberglass wool has an R value of 3.3, are examples of materials which have good resistance. The heat transfer coefficient, or the U value shown as U in the previous equation, is equal to the reciprocal of the resistance. It is a measure of heat flow over an unit area of a material. The higher the U value, the more heat is transmitted. Let's look at an example of how to calculate the heat gain or transmission. From the roof construction shown, calculate the heat gain through the roof and ceiling if the ambient, unconditioned room temperature is conditioned at 23 degrees Celsius and the outdoor temperature is at 35 degrees Celsius in summer. Assume the roof area is 90 square meters. Observing the table, we can see that there are 6 elements or materials in this setting. Their resistance values, or R values, are listed in the table to the right. Remember, Q is equal to the product of the coefficient of heat transfer, total surface area, and the temperature difference across the material. The total resistance will be the sum of all the material's resistances, and total heat transfer coefficient is a reciprocal of the total resistance, or 1 divided by the total resistance. Firstly, the total resistance will be the sum of the resistance for each material. The values can be found in the previous table, and the sum is 2.76 meters squared Kelvin per watt. Therefore, the heat transfer coefficient is equal to 1 divided by 2.76, which equals to 0.36 watts per meter squared Kelvin. So the energy transferred will equal to 0.36 watts per meter squared Kelvin multiplied by 90 meters squared, times the change in temperature from 308 to 296 Kelvin, remembering that when calculating the heat transfer, you must convert degrees Celsius to degrees Kelvin. To convert, add 273 to the degrees Celsius value. The energy transferred is 388.8 watts. What is important to understand here is that the internal thermal performance of a space is significantly affected by the resistance value of the materials used to enclose it. The higher the resistance, the less temperature fluctuation, and the easier it is to condition the space, which, at the end of the day, means less energy used in cooling or heating. Now that we have an understanding of how heat works, we'll address HVAC systems to discuss where efficient climate control can be achieved, starting with traditional air conditioning systems. Traditional air conditioning systems, and in fact most HVAC systems, work on the basis of a refrigeration cycle. In order to understand air conditioning, one must understand the refrigeration cycle. The refrigeration cycle essentially employs the laws of heat transfer to displace or shift heat in a system. Air conditioners consist of 4 main components: the compressor, which is the main energy user, the condenser, which emits heat to the external environment, the expansion valve, which reduces the pressure in the cycle, and finally the evaporator, which removes heat from the space. The compressor provides energy input to the refrigeration cycle. The size of the compressor is determined by the following three things: volume of the refrigerant being circulated, its properties, and the increase in pressure from the evaporator to condenser. In the compressor, a refrigerant, usually a gas, is compressed such that a rise in its pressure equates to a rise in its temperature. All refrigerant cycles use a refrigerant to complete the refrigeration cycle, and we'll look into this later. The condenser is a heat exchanger that rejects the heat from the system, accepting hot, high-pressure refrigerant and changing its state from a vapor to a liquid. In larger plants, the most common type of condenser used is the evaporative condenser, or cooling tower, whereas in small plants, air-cooled condensers are most common. Both types of condenser require free circulation of air over the coils for effective cooling. The condenser, usually installed externally to the building, allows the generated heat to dissipate and be lost to the environment. Fans mounted on the condenser unit are used to draw the cooler external air through the hot condenser coils. At this point, the gas will condense to a liquid at high pressure. The expansion valve maintains the pressure differential between the evaporator and condenser. The thermostatic expansion valve is used in small and medium-scaled applications. A regulator valve sets the pressure and the temperature in the evaporator. The high-pressure refrigerant liquid reaches the expansion valve, having come from the condenser. The valve then reduces the pressure of the refrigerant as it passes through its orifice. Essentially, the liquid will flow from the high-pressure side to the low-pressure side. The evaporator turns the liquid refrigerant into a vapor by evaporating the liquid. It can also be considered as a heat exchanger as it transfers heat from the coils to the refrigerant. It consists of sets of coiled tubes where the refrigerant is contained. The cooling capacity of the evaporator depends on the surface area of the coils and the temperature difference between the refrigerant and the air being cooled. As the refrigerated fluid moves through the evaporator, an evaporator fan draws air across the coils and distributes it from the head unit into the space to be cooled. As it does this, the air loses heat to the refrigerated system and becomes cooler. Inversely, the refrigerated fluid heats up and vaporizes, and returns to the compressor to begin the cycle again. Generally, refrigeration cycles rely on a refrigerant, which is a fluid that absorbs heat while undergoing a phase change in the evaporator and releases energy while compressed at a higher pressure and temperature in the condenser. It is essentially the medium of heat transfer. A refrigerant's suitability depends on many factors, which include its thermodynamic properties, physical and chemical properties, its safety, and the effects on the environment. There are four classes of refrigerants. These are halocarbons, hydrocarbons, organic, and inorganic. Choosing the correct medium depends on a few factors, such as total cooling load of the building, the type of building and application, and the building life expectancy. In chilled water systems, water is used as the heat transfer medium to cool the air. The water is cooled by a chiller, which uses a refrigerant to achieve this. These usually have a much higher capital cost due to the additional equipment such as chillers, pumps, and pipework, and therefore these systems are generally only used in larger applications. They are, however, more efficient and have a longer life expectancy than other refrigerant systems. Whereas for direct expansion systems, the refrigerant itself is pumped to air handling units from the compressor and the heat transfer occurs from the air to the refrigerant directly. These are more suitable for smaller applications due to their lower capital costs and less maintenance required. There are two types of refrigeration models: cyclic and non-cyclic. Cyclic models can be divided into vapor cycle and gas cycle, and the vapor refrigeration cycle can be further divided into vapor compression refrigeration cycle and vapor absorption refrigeration cycle. In cyclic refrigeration, the heat is removed from the low temperature space and rejected to a high temperature sink with the help of external work. The vapor compression refrigeration cycle is where the vapors of a refrigerant are compressed by the compressor to achieve cooling. The basics of this cycle were discussed earlier. The vapor compression refrigeration is the cycle most commonly used, including in domestic refrigerators. They have a higher coefficient of performance than the vapor absorption cycle. Vapor absorption refrigeration uses water-ammonia systems. In this system, there is no compressor but instead an absorber. The system generally works like this. Ammonia is dissolved in the water, then this mixture is pumped and heated, increasing the temperature and pressure of the ammonia. The ammonia then leaves the absorber at a high temperature and pressure to complete the rest of the refrigeration cycle. In this system, minor energy is consumed by the pump, reducing electricity costs. However, heating is achieved by the steam, which requires an additional source of heat to produce. Vapor absorption is mainly used in industries where there are very large stocks of steam available. The cycle is more effective where large-scale refrigeration in excess of at least 20 tons is required. The gas cycle is very similar to the vapor compression cycle, however the refrigerant used is gas. There is no condensation or evaporation, meaning that there is no phase change in the refrigerant. It stays as a gas and does not change to a liquid. Heat exchangers are used to increase and decrease the temperature of the gas. The gas cycle is not as efficient as the vapor compression cycle as it needs a larger amount of gas to achieve the same cooling effect compared to a liquid refrigerant. The non-cyclic refrigeration cycle achieves cooling by melting ice or subliming dry ice. These methods are usually used in a small-scale refrigeration, such as in laboratories. Sublimation is when a solid converts directly to a gas, skipping the liquid phase. Frozen carbon dioxide is an example of a substance that can do this. Now that you understand the basics of the refrigeration cycle, we will look at split, ducted, and window and wall air conditioning systems, as well as cooling towers, as these are by far the most common technologies found in residential and SME applications. Split systems are capable of being installed locally in a single room, or also in larger areas using multi-headed split systems. Window wall units operate in the same principle as the split system. Ducted systems can be installed as a network to condition an entire building or house uniformly, and cooling towers are mainly used in larger buildings or industrial applications as part of the refrigeration cycle. Split systems are capable of being installed locally in a single room to cool or heat a small space, or also in larger areas using multi-headed split systems. It is able to perform both cooling and heating cycles. The compressor and condenser unit is situated outside, and the head unit housing the evaporator is situated inside, circulating the air. Window or wall units come as a packaged system where the refrigeration cycle is essentially performed internally. They can be installed to sit through a window or wall opening with interior controls. They are used to cool a small space and operate under the same principles as the split system. Ducted systems can be installed as a network to condition an entire building or house uniformly. This system has the capability of selecting specific controls for specific areas or rooms or zones. Ducted systems are relatively quiet and efficient, with three main components: the outdoor section, the indoor ducted section inside roof space, and the zone control. Again, it is capable of performing cooling or heating cycles. Cooling towers are used in larger buildings and industrial applications. Cooling towers dispose of unwanted heat to the atmosphere by reducing the temperature of water circulated through condensers or other heat rejection equipment. The common type of cooling tower used in air conditioning applications is the counterflow mechanical draft tower. Split and ducted systems are by far the most commonly used air conditioning systems in Australia, particularly at the residential and SME scale. It can be tricky to determine which system is best for each application, but this table lists a few of the major pros and cons for each. Notably, split systems are usually installed to operate in single rooms or small spaces, however they can be installed to multiple head units to take advantage of several small spaces. Ducted systems can be installed in zones as previously stated, where you can condition selected areas or an entire dwelling. Both types of systems are generally able to run cooling or heating procedures. Split systems can be installed after the house or the building has been built, however ducted systems are usually implemented in the building design and structure and have high installation and maintenance costs, though they can be installed retrospectively. It's necessary though to ensure that there is sufficient ceiling space if you're looking to suggest installing ducted AC. The biggest benefit of a ducted system is its ability to control specific zones or spaces. You can heat or cool your entire house or just specific rooms. Essentially, you would use split systems in smaller spaces and ducted systems in larger areas where conditioning diversity is required. To calculate the amount of power required to perform this cycle, we'll return to the basic equation for kilowatt hours per annum. The base calculation states that annual kilowatt hours is equal to the circulated power divided by the efficiency of the system multiplied by the time for which the system is run per annum. In this instance, it is possible to calculate this in two ways, using either the EER or COP. To determine the efficiency and performance of a refrigeration system, two dimensionless numbers are required. These are the energy efficiency ratio and the coefficient of performance. The energy efficiency ratio, or the EER, measures the energy efficiency of the cooling performance. It's calculated by dividing the rated cooling capacity output by the cooling input power. The coefficient of performance, or the COP, measures the energy efficiency of the heating performance. This is equal to the rated heating capacity output of the unit divided by the heating input power. There is a relationship between the EER and the COP, which means that the COP is equal to the EER divided by 3.412. Another relationship that takes into account the power and the demand is kilowatt per ton is equal to 3.52 divided by the COP, or kilowatt per ton is equal to 12 divided by the EER. Generally, it is not important to understand the math, as the EER and COP values are available from the unit manufacturer. However, using the equations from the previous page, the kilowatt hour can be calculated by manipulating the equations. Kilowatt hours will equal 3.52 multiplied by the ton required divided by the COP of the unit, or 12 multiplied by the ton required divided by the EER of the unit. The ton is a unit of measurement of the quantity of air conditioning required in the space per hour. 1 ton of air conditioning is equal to 12,000 BTU per hour. 1 BTU, or British thermal unit, is approximately the energy required to heat 1 pound of water from 3.8 degrees Celsius to 4.4 degrees Celsius, or the equivalent in Fahrenheit. A refrigeration ton is the amount of heat removed by an air conditioning system that would melt 1 ton of ice in 24 hours, and is equal to 12,000 BTU per hour. When converted into the metric system, 1 ton of air conditioning is equal to 12,661 kilojoules per hour. The EER and the COP are essentially values for efficiency. Using the EER value, the equation can be modified so that kilowatt hours per annum is equal to 12 multiplied by the demand in tons, all divided by the ratio of the output cooling power and the input cooling power. Similar manipulation of the equation can be completed to use the COP value. Kilowatt hours per annum is equal to 3.522 multiplied by the demand in tons, or BTU divided by 12,000, all divided by the ratio of the output heating power and the input heating power. Heating and cooling capacity and input power can be found either in the unit's manual or specification, or on data tags often located on the right side of the internal head unit for window and wall or split system units, and on the external unit for all the HVAC types. However, while internal unit data tags will often detail both output power, also known as capacity, and input power, external units often only specify input power. When faced with a HVAC system in an audit situation, it is important to understand how to calculate the energy use represented by the system. Here we start again with the base calculation. Annual kilowatt hours is equal to the calculated power, divided by the efficiency of the system, multiplied by the time for which the system is run per annum. As energy efficiency is essentially a product of reducing the total kilowatts of a system, it can be achieved through either reducing the power, increasing the system efficiency, or decreasing the time of use. First, let's look at reducing the power of the system. Required kilowatts is equal to 12, multiplied by the demand, divided by the ratio of the cooling output power and cooling input power. Removing the elements which can't be influenced, and the elements which influence efficiency and time, will allow us to see what opportunities there are for reducing the required power. These are the constants 12 and 12,000, and the cooling capacity and input power. We can see that the demand of refrigeration or air conditioning is the main element that will essentially affect the power consumption of a unit. The BTU requirement of a space is essentially a result of the energy required to condition a space with certain characteristics. The most efficient way, then, to reduce the required power is to address those factors which limit the effectiveness of cooling or heating in a space. Some ways in which this can be done include reducing the demand or volume of space, insulating the area so that the heat is stored or transferred, removing or mitigating large sources of heat where possible, removing or mitigating losses such as leaks, and reducing solar gain. Reducing the amount of space or area that requires conditioning will reduce the amount of air conditioning required. It is essential that only the occupied spaces are conditioned. Many ducted systems allow clients to set the correct thermostat settings for the different zones or spaces and for the relevant weather seasons. Insulating a building or dwelling can provide major cost savings in energy bills. Appropriately insulating a building will provide year-round comfort, reducing both cooling and heating bills by up to 50%. Insulation can be installed in the walls, roof, and floor using materials with high resistance or high R values provide the best insulation. Window glazing also has a major impact on the energy efficiency of the building envelope. Glazing can decrease the amount of heat entering or leaving the building and can reduce cooling and heating costs. Reducing solar gain involves the installation of shading, be it either mechanical or natural. This includes installation of eaves, louvers, or awnings to reflect the heat or natural shading, such as planting around the building to provide shade. Installing thicker and light-colored curtains will also help reflect the heat that enters through windows. The orientation of a building's windows will also affect its solar gain. For example, northern windows receive more solar radiation than southerly windows in Australia, and more in winter than in summer. However, it is important to remember that a healthy working environment should always have access to sunlight to ensure the well-being of its occupants. Reducing or removing the sources of heat will also help in reducing power consumption. This can be achieved by removing unused or unnecessary electrical equipment that is connected, reducing the amount of occupants in the space, glazing windows to reduce the heat gain, and painting the roof, ceiling, and walls in a light reflective color. Energy efficiency can also result from an increase in the efficiency of a system. Let's isolate the elements that relate to efficiency, which in this instance is the energy efficiency ratio, or EER. The required electrical input power and capacity of a unit is generally predetermined by all other efficiencies and power requirements. That is to say that the requirements and parameters of the room being conditioned are determined as a priority, and then a unit size is selected to deliver to that value. However, there is still an opportunity to improve efficiency for the way in which cooling is delivered, most significantly in variable speed devices and inverter technologies. Inverters use a variable frequency drive, or VFD, that includes an adjustable electrical inverter to control the speed of the compressor's motor, and therefore the cooling output. Essentially, it gently increases or decreases the power input to the motor, and once reaching the required temperature, maintains the power input steadily. This prolongs the life of the motor and compressor, saving energy and efficiency at the same time. An air conditioner with an inverter technology is generally 30 to 50% more cost efficient to run than one without. The Australian and New Zealand governments have introduced the MEPS scheme for air conditioning units imported and manufactured in Australia. Specific units are required to meet the minimum energy performance standards. In general, the requirements are for three-phase systems up to 65 kilowatts of cooling, for non-ducted and ducted, both residential and commercial units using the vapor compression cycle. In addition, all one-phase systems, non-ducted and ducted, commercial or residential units, also using the vapor compression cycle, are included in the requirements. In 2010, the algorithm for calculating AC system star ratings was updated, expanding the possible numbers of stars from 6 to 10. The rating also now takes non-operational energy use, such as standby power, into consideration. For a full detailed list of all requirements, please see Australian Standard 3825.2, 2011, Performance of Electrical Appliances, Air Conditioners and Heat Pumps, Energy Labeling and Minimum Energy Performance Standard Requirements. Behavioral changes are also a significant factor in the effective use of an air conditioning system. By reducing the time of use, we can significantly decrease the total kilowatt hours consumed. In addition, minimizing the running time of any equipment, especially in commercial sectors, will increase the potential life of the asset, therefore reducing maintenance costs. Time of use can be decreased by installing sensors and monitors and managing standby power consumption. Considerable energy is wasted due to climate control being left on unnecessarily when occupants leave the home or building. Occupancy or time of use sensors reduce energy consumption by installing intelligent controls to only operate air conditioning and ventilation when required. A cost saving of up to 20% can be expected. To accurately reflect the total annual power use of an appliance, one must also consider the power used while in standby mode. Standby power is energy used by an electrical device while connected to a power source but not in operation. Standby power in households can account for 10% of energy use. This could be more for certain businesses depending on what appliances and other electrical processes they use. Australia is leading the way in addressing standby power issues, with the Australian Ministerial Council on Energy publishing a world-first national standby power strategy in 2002, which aimed to reduce appliance standby power consumption to under 1 watt by 2012. There are two commonly identified standby modes. Passive standby is where the appliance is in its lowest power-consuming mode and can be detected by an LED light, clock, or where the device is waiting to be switched on by remote. Active standby is where the appliance is on, but not performing its main function. A device is usually only completely off when it is switched off at the wall, as devices can still consume very small amounts of power even when they are switched off at the device's power switch, if it has one. To calculate the total energy consumed annually, simply multiply the real power of the appliance when in use, in kilowatts, by the number of hours it is active per annum, and add it to the real power of the appliance when in standby by the number of hours it is in standby per annum. Fans and exhausts. Fans can be an excellent alternative to traditional HVAC technologies. Fans, however, only circulate air, they don't reduce the temperature. The common household fan will consume no more than a maximum of 65 watts, and there are efficient ceiling fans available from companies like Opal Air that use as little as 39 watts. These types of fans are economical because of their low running and installation costs. Industrial fans are selected based on the volume, flow rate, and pressure required, space limitations, and efficiency. The two main types are centrifugal and axial fans. In centrifugal fans, the air changes direction when entering and secondly when leaving. In axial fans, there is no flow direction. The common blower achieves higher pressures than fans and is therefore not necessarily considered a fan. Here is a comparison of the different types of fans, their characteristics, and applications. Again, we take the base calculation of annual kilowatt hours is equal to the calculated power divided by the efficiency of the system multiplied by the time for which the system is run per annum. Fans and blowers can essentially be considered as pumps where efficiency is concerned. Both work by directing a volume, in this instance a gas, through changes in pressure, and in both cases efficiency is an expression of the ratio of power gained by the volume to the shaft power supplied. As with pumping systems, power consumption can be reduced by reducing the demand and size of the fan system. This will depend on the size of the space or building, the flow rate that is required, and the size of the fan impellers. Reducing the pressure difference between the fan outlet and inlet will also reduce the power consumption significantly, as well as the amount of air leaks in the air conditioning system. If air leaks through, the system is overworking unnecessarily, imposing extra work on the fan motor. Reducing the amount of usage time will also reduce the power consumption. As per any other air conditioning system, fans should only be used when required. Though relatively minor by themselves, the effects of wear on any equipment can significantly reduce the operating efficiency. Fans should be regularly checked for appropriate clearances between the housing unit and the impeller, minimizing in leaks and out leaks in the air conditioning system. It is important that all fans are frequently maintained to ensure they operate efficiently. If required, a more efficient fan should be installed or retrofitted. Radiant technologies. Radiant technologies are considered alternate technologies, yet some of these can actually be more effective than conventional air conditioning equipment. Radiant air conditioning employs the laws of radiant heat transfer to cool or heat a space. Of note are chilled water beams, radiant heaters, and in-floor heating and cooling. In chilled water beams, cold fluid passes through the beam in much the same way as refrigerated fluid moves through a traditional HVAC system. As the chilled water passes through the beam, it draws the heat from the air, heating the liquid and cooling the air. This can be used as a supplementary source of cooling, typically saving up to 20% of overall air cooling costs. Chilled beams have a lower operating cost and energy consumption than traditional HVAC systems of the same size, though the energy savings depend on the climate in which the installation is located. If integrated with the structure and design, chilled beams can provide lower installation and life cycle costs. However, concerns regarding the potential for condensate formation on the cold radiant surface, which results in water damage, mold, and the like, means that the system is not as commonly utilized as perhaps it should be. There are two common types of radiant heaters, oil-filled heaters and bar heaters. The oil-filled heaters are generally electrically powered. These units heat the oil inside the column or oil reservoir which radiates heat. They usually come with thermostat settings for easy adjustment. Bar heaters operate in the same principle, where an electric current passes through an element which is heated and electrical energy is converted to heat. They provide quick and intense heat which makes them effective in small places. These types of radiant heaters have poor efficiency and result in higher operation cost. However, they are moderately cheap to purchase and their portability makes them effective in some small applications. In-floor heating and cooling systems are systems in which electrical resistance elements or hydronic fluid piping are installed underneath a building's floor space to heat or cool respectively. This type of system is sometimes used in major sporting fields to condition the turf, or for the melting of ice on landing pads or driveways in cold locations. This system works in much the same way as a chilled beam, however it has two key differences. Firstly, this system can be used either to heat or cool, depending on the setup or use of the refrigeration cycle. And secondly, in-floor systems make use to the thermal properties of the flooring materials to either store or dissipate heat where appropriate. The element or piping spacing, the surface conductivity, the type of floor covering, and or the soil moisture content all take effect on the efficiency of an in-floor system. In-floor systems can be extremely effective over large open areas where ducted air conditioning may not be feasible, such as areas with higher ceilings, in particular when coupled with solar or geothermal power. The key drawback of this system, though, is access for maintenance and installation, of which there is practically none once a floor has been laid. The electric heating in-floor system uses non-corrosive heating elements like cables, bronze mesh, and carbon mesh to transfer the energy. It is usually a simple installation during the construction of the building. The cooling system, or hydronic system, has a piping network installed below the concrete floor. Usually water or a mixed substance is circulated between the floor and the boiler or heat pump when cooling. This system, however, requires a more skilled installer due to the boiler or chiller components. Burners and fireplaces are a more traditional form of heating used in Australian homes. They can be built into the house or freestanding. Current models are subjected to an energy efficiency star rating as per the Australia Standard 4553 gas-based heating appliances. The burners can be supplied to operate with LPG or natural gas. Other additional features available throughout the market are full electronic thermostat control, timers, auto off and economy functions, manual heat control, and preheat features, and also child safety locks. Traditional fireplaces obviously do not consume generated electricity and therefore come at a less of a cost to clients, though also at a less of convenience. Passive technologies. Passive technologies can often completely replace or supplement a mechanical ventilation system, depending on the climate. Passive conditioning technologies are essentially passive ventilation technologies which employ existing resources and heat transfer properties to cool a space naturally, with little to no electrical assistance. They include evaporative cooling, trom walls, and wind tunnels, like Federation Square's Labyrinth system. Evaporative cooling is one of the oldest forms of cooling. Whenever warm, dry air passes over a cool body of water, tiny droplets of water are vaporized, exchanging heat, and effectively cooling the air. These principles are often employed passively by placing bodies of water in the path of warm winds, but can also be integrated into low-energy systems which employ a fan to distribute cooled air. Understandably, evaporative cooling performs better under certain conditions, specifically when relative humidity is low and temperature is high. Wind tunnels employ long tunnels which draw cool winds through or under buildings. As the cool breezes pass through the tunnels, heat is lost from the thermal materials to the cooler air, consequently reducing the temperature of the building materials. The Labyrinth system is a new, innovative method implemented at Federation Square in Melbourne. The system is directly below the building, with a size of 40 metres by 40 metres and approximately 1.2 kilometers long. The system uses corrugated concrete walls which have an increased surface area to absorb the heat in the space. As the air is passed through the labyrinth cells or tunnels, they are heated or cooled depending on the time of year. This system can deliver up to 12 degrees difference between internal and external ambient temperature. Since 2003, the building has achieved a 19.6% reduction in energy consumption. Trom walls use convection to either heat or cool a space depending on thermal conditions. Trom walls are essentially a solar chimney which, when heated, creates a convection current of rising air that draws warm air from a building and vents it out through the facade. It works similarly when heating a building, pushing cold air out. Other features can be added to Trom walls. Nowadays, electric blowers controlled by thermostats are incorporated to improve air and heat flow. Some have fixed or movable shades, while others have windows installed. Windows reduce the efficiency, but do allow for natural lighting to enter the space. An example scenario. Question number 1. A 10-ton cooling rooftop air conditioning unit has a EER of 8.5. A. Find the COP, and B. Find the kilowatt input load at full capacity. For part A, the COP will be equal to the EER divided by 3.412. Therefore, the COP is 8.5 divided by 3.412, equaling 2.49. For part B, the kilowatt input is calculated by dividing 12 by the EER, which is 8.5, and multiplying by the total refrigeration ton, which is 10. This equals 14.12 kilowatts. Question number 2. How many kilowatt hours are used to provide 90 million ton hours of air conditioning with a system having a COP of 3.0? Use the equation kilowatt hour per ton hour is equal to 3.517 divided by COP. Using the requested equation, we can manipulate it so that kilowatt hours is on its own on the left side. Kilowatt hours will be equal to 3.517 multiplied by the refrigeration ton hours, all divided by the COP. Substituting the values into the equation, this equals 105.5 times 10 to the power of 6 kilowatt hours. Example 3. A. Calculate the kilowatt hour per annum if a split system air conditioning unit is used 9.5 hours a day on average, 5 days a week, for 48 weeks a year. The rated capacity is 9.4 kilowatts and the input power is 2.88 kilowatts. The BTU demand is equal to 24,000 BTU per hour. B. If its passive power consumption is 0.5 watts, what is the total power consumption of the appliance? Assume that it is on standby for the 48 weeks only. For part A, we firstly calculate the demand, total time, and the EER. Converting the demand to ton will equal 24,000 divided by 12,000, which is 2 ton. The total time of use is 9.5 hours, multiplied by 5 days a week, multiplied by 48 weeks. This is a total of 2,280 hours per annum. The EER is equal to the rated capacity divided by the input power, which is 9.5 kilowatts divided by 2.88, and that equals 3.26. Secondly, the total power consumption is calculated. The total power consumption in kilowatt hours will equal 12 multiplied by 2 ton, all divided by the EER, which is 3.26, all multiplied by the total time, 2,280. The total kilowatt hours will equal 16.785 kilowatt hours per annum. For part B, firstly we calculate the total standby time per annum. It will be the summation of the weekly time multiplied by the number of weeks. The weekly time will be 2 full weekend days plus the remainder of the days in the working week where the appliance is not in use. The total standby time is 5,784 hours. The second stage is to calculate the total amount of watts consumed during standby time. Total power is 0.5 multiplied by 5,784 hours, which is 2,892 watts or 2.892 kilowatts. To finish off, sum the active power and standby power to obtain the total power. total power will equal 16.785 kilowatt hours of active usage plus 2.892 kilowatt hours of standby time. This is 19.677 kilowatts hour per annum. Question number 4. What is the actual energy consumption of a wall-mounted air conditioning unit if its rated power is 8 kilowatts and its efficiency is 65%? The energy consumption will equal the rated power divided by efficiency, which is 8 kilowatts divided by 0.65, which equals 12.3 kilowatts. To continue with presentations, please select Energy Session 6.0, Water Heating, from the navigation bar. To complete the assessment for this presentation, please select Tutorial 5.0, Thermal Performance and Climate Control.